Hello, my name is Abdurrahman Azab. I work at the University of Oslo, Center of IT. I'm leading the lightweight containerization service in PRACE-6IP, and I'm presenting the lightweight virtualization by PRACE for large-scale HPC. This is a lightweight virtualization service by PRACE, and there are several partners: University of Oslo, University of Ljubljana, CSCS in Switzerland, CEA, CISGA, LRZ, Shinega, UHEM, INRIA, Scenario. Motivation: this service is about lightweight containers and Uni Kernels. With Linux containers, software installation can go as follows. I need a software X, and the software is installed and ready as a Docker image somewhere. The system administrator can just pull it and get it to the system. Even the user can get the software installed and run it on the system. Without containers, the users need to ask the system administrators to install the software. Otherwise, they need to pull the software and run it in their home directory. And there are many issues that can happen with this scenario. So with containers, it is built once, run everywhere. Someone could run a software that is for Ubuntu, run it on CentOS, and vice versa. There have been some issues before regarding security. Now security is covered with CLinux, with syscall whitelist, and capability whitelist, and user namespaces. So containers are not insecure, but it depends on the configuration whether it is secure or not. So they can be fully secure. In this service, in 6IP, we explored several container platforms, including Singularity, Saros, Peacock, which is a containers and virtual machine platform, Docker, Podman, En-route by NVIDIA, uDocker, and Containerized HPC. This is not a runtime for containers, but using containers as HPC nodes. And we supported 23 use cases with different disciplines: data analytics, deep learning, machine learning, and others, and several use cases with virtual machines and containers, and shared memory and distributed memory. In the first phase in 5IP, we explored some container platforms like Singularity and Docker. And in 6IP, we explored new container platforms like Saros, developed by CSCS. Saros combines container portability with native HPC performance. And it is similar to Docker. It pulls regular Docker images. And this is how it works. One creates a Docker image on the laptop, push it to Docker Hub, go to the HPC system where Saros is installed, pull that Docker image, and just run it. And here, if for those of you who know Docker, these are the Saros commands. This is for pulling a container or a container image from a public repository, similar to the Docker pull, and then load if you have the image on a file, and list the images and remove the image and run. This is similar to the Docker commands. Another technology that we worked on in this service for HPC, Uni Kernels. Uni Kernels are different from virtual machines and different from containers. It has both advantages. The advantage of lightweight, so it does not contain all of the software bloat of the virtual machine. It contains only what is necessary. For the application, no more binaries, for the kernel, not the whole Linux kernel, but just as a very thin OS layer. It's single purpose, run one application, single process, and single binary. There are a lot of benefits. Lightweight virtualization contains only what is necessary, and pre-application tailored kernel, and reduced OS noise and increased performance by reducing system calls. There are several types of Uni kernels, pure memory safe languages, C or C++ if you want to do some development, various levels of binary, and Rust or Go Uni kernels. And there are the links for different types of Uni kernels. Everything can be found here in the unikernel.org. For the performance, we have faster system calls, and these are benchmarks here comparing Ubuntu to OSV, which is a Uni kernel. You see how much is the difference, millions of transactions per second. And this is Hermitox with different architectures comparing to native Linux. And it also has reduced kernel noise because of the less layers. Security-wise, it has much less system calls because it does not use the actual kernel. It has its own kernel. The advantage of it over virtual machine that it is lightweight. So containers are lightweight but not secure because they have a lot of system calls. Virtual machines are secure but not lightweight. Uni kernels are lightweight and secure. There are some challenges with Uni kernels: compatibility, less support for SMP or OpenMP, not support for the drivers of InfiniBand and GPU drivers. So they are not that mature yet. So it needs some more work, and also for big companies like Mellanox and NVIDIA and other companies to create drivers for Uni kernels to their hardware. Another work that we had in this service is containerized HPC. What is this? To run the HPC system, the cluster, in containers. So we tried this on a Condor cluster, and we called it GIOC, Get Your Own Containerized Cluster. So this is the HT Condor central manager, runs in a container, and all the compute nodes run as Docker containers. And this is in a Swarm cluster. And Docker Swarm is the distributed orchestrator that comes together with Docker Engine. Inside those containers, the compute nodes, which are the executors of the HT Condor cluster, run as containers, and they can run the jobs internally as containers, either Singularity or Docker containers. So all the compute nodes can connect to Singularity repository or Docker repository. What is nice about this is that using the Swarm commands, you can extend or shrink the number of compute nodes. And you can have several HT Condor clusters in the same swarm, and several swarms, and all of them, they are connected to the same repository for Singularity containers or Docker containers to get them to run into your clusters as jobs. And this is also another example of elastic cluster, and here it shows how the elasticity can work. So this is the number of nodes, and this is the job queue. When you have a lot of jobs in the queue, starting to initiate more nodes. First, there was no compute nodes. Now it is increasing. And then when the no more jobs are waiting in the queue, then the number of compute nodes is reducing, not needed anymore. And when we push another chunk of jobs, more nodes are created. Now they are all executed, and another chunk of jobs. Now all the jobs are done, finished, then the nodes will be killed so that we don't need these elastic nodes. There are several applications to this. We implemented this with a front end Galaxy server. So this is a user-friendly web interface that connected to an elastic compute cluster that runs on sensitive data computation. So the researchers can easily run their computing on this sensitive data cluster. And this is how the elasticity work. So now we have 3 physical nodes, which are the swarm nodes. And here is the HT Condor cluster. This is the front end, and these are the executors. This is the front end and the central managers. So this is the command for creating compute nodes. Docker service scale. So now I want 5 compute nodes, and now I have 5 compute nodes, all of them running as containers. And if I want to see the number of compute nodes calling the queuing system to list the actual compute nodes, Condor status, execute, Docker execute inside the container that has the front end and the central manager, Condor status, it lists the compute nodes from the queue. Yes, this is part of our work in the lightweight virtualization service.